Hi everyone, welcome back to the channel. In this video, we shall try to learn about the concept of liquid crystals. And let us directly enter into the topic. So we know that in the nature, a matter do exist in three phases. That means it can exist in a solid state, it can exist in a liquid state, or it can exist in the form of vapor. And one state of the matter can be easily changes into other matter that we are well known. That is, when a solid material is subjected to the process of heating, solid will get changes into liquid. And when the liquid form of the same matter is further heated, then it gets changes into the form of vapor. But when you perform the reverse process, that means instead of heating, if you cool, the vapor form of the state can be converted into liquid, and when the liquid form is further cooled, means when you drop the temperature, the liquid form will once again changes into solid state. So that we are well known, that is melting, vaporization, and like this. The reverse process also we can say. But we are having certain solid materials, when they're heated, instead of going into the form of liquid directly, we will observe two-phase transformations for a solid material. That means solid, when subjected to the process of heating, it won't produce the liquid form directly. Before the liquid, the solid material do show one other phase transformation. That means when a solid material is heated, before going to the complete liquid state, that is to the form of a true liquid, the solid first changes into a turbid liquid. It's not a true liquid, it converts into a turbid liquid. And when that turbid liquid is further heated, then we are going to get the true liquid state. When you subject the true liquid which is obtained to the process of cooling, again the true liquid will again changes into the turbid liquid form, and the turbid liquid form on further cooling will changes into solid state, and the temperature will remains the same for the interconversion of solid and turbid liquid, as well as for the interconversion of turbid liquid and the true liquid form. And here you can observe between the phases of a true crystalline solid and a true liquid, we are observing presence of a turbid liquid, and this turbid liquid is actually translucent in nature. That means this turbid liquid is not that much clear, transparent like a true liquid. That means the turbid liquid is semi-transparent, but not completely transparent like a true liquid. But when you check out the characteristic property of the turbid liquid which is obtained firstly when the crystalline solid is heated, this turbid liquid do exhibit the property of anisotropy. That means the turbid liquid will not show the same value for its physical properties when measured in different directions. That means will give different values for its physical properties when measured in different directions. That is the actual meaning of anisotropy. This turbid liquid is exhibiting the property of anisotropy, which is not at all the characteristic property of a true liquid. Remember, the true liquids are always isotropic in nature. That means they exhibit same values for their physical properties irrespective of the direction of measurement. But this turbid liquid is anisotropic in nature, which is not the property of a true liquid, and the anisotropy is the clear property of a crystalline solid. That means the turbid liquid, see the name itself telling you, it is a liquid form, means which is having capability to flow like a liquid. But since it is exhibiting anisotropic properties, that means this turbid liquid is an intermediate form between pure crystalline state and a true liquid. Such an intermediate state is simply called as mesomorphic state. Mesomorphic state, it's a Greek word, mesomorphic, in the sense it is the intermediate form between that of solid and, I mean to say, pure crystalline solid and true liquid. And such mesomorphic state which exhibiting the properties of both crystalline solid and true liquids are simply called as liquid crystals. So liquid crystals or the materials, or it is an intermediate form of pure crystalline solid and a true liquid, and which exhibit the properties of both crystalline solids such as anisotropy and that of pure liquid such as fluidity. So like a liquid, a turbid liquid will show fluidity, and like a pure crystalline solid, it exhibits anisotropic character. That's why we are calling them as liquid crystals. Okay, so but instead of using the word liquid crystals, it is far better to go with the word mesomorphic state, which indicating the intermediate form. But in majority of the context, we use the word liquid crystal only instead of mesomorphic state. And if you come to the development of liquid crystals, the first and foremost liquid crystal which was generated in the field of liquid crystal science is cholesteryl benzoate. Cholesteryl benzoate is the first material which is observed to show the property of liquid crystals, and this cholesteryl benzoate is having the formulae C6H5COO C27H45. It is the molecular formula of cholesteryl benzoate. When this cholesteryl benzoate C6H5COO C27H45, when it is heated, say at a temperature of 145 degrees Celsius, it changes into the form of the turbid liquid, that is to the form of liquid crystals. So it is the pure solid form, and here it changes into the liquid crystalline state. And when the liquid crystalline state is further heated, say at a temperature of 178 degrees Celsius, it changes into the true liquid form, but the molecular formula remains the same. So it is the pure liquid state. When the liquid state of this cholesteryl benzoate is further cooled, say at the same temperature, once the temperature reaches to 178 degrees Celsius, again it changes into the liquid crystalline state. And when you cool further, say at 145 degrees Celsius temperature, again the liquid crystalline will get changes into the solid form. Means they are interconvertible materials. Only the thing is the temperature is required. And regarding this liquid crystalline science, the more contribution was given by a French physicist by name P.G.D. Gens. He is a French physicist who gave a much of contribution towards the liquid crystals and the polymers framed from that of liquid crystals. And by honoring his work in the year of 1991, P.G.D. Gens awarded with the Nobel Prize. So he is a person who received the Nobel Prize for his work in liquid crystals. Not only the chemical materials, the biological materials also do exist in the state of liquid crystals. Say, whatever the food we consume, it mainly consists of proteins and fats. These things, once we consume the food, whatever the proteins and fat material which is present in the food material will exist, or will they get changed? They will get changed into the form of liquid crystalline state before they undergo digestion. Before digestion, they get changes into the form of liquid crystal. And when the proteins and fats before digestion, when they get changes into the form of a liquid crystal, then that helps much more for their easy absorption into the body. So absorption will be easy by the body, so that the proper utilization of proteins and fats by the body will become easier when they get changes into the form of liquid crystals. And here you can observe, at one temperature we are converting the solid material into the form of liquid crystalline state, and on further heating the liquid crystalline state is changing into the true liquid. The temperature at which the solid material get changes into the liquid crystalline state will be called as transition temperature. Transition temperature. The temperature at which a pure crystalline solid get changes into liquid crystalline state, and the temperature at which the liquid crystalline state will get changes into true liquid, and that temperature is actually called as the melting point of that particular melting temperature, or melting point, whatever you can say. So the temperature at which the pure crystalline solid get changes into liquid crystalline state is called transition temperature, and the temperature at which the liquid crystalline state get changes into true liquid is called melting temperature. And the materials which are having capability to exist in the form of liquid crystalline state are very much stable, because they will not undergo decomposition, since they are not directly changing into the liquid. Before to that they are changing into the form of liquid crystalline state. That's why the easy decomposition of those materials are not possible. Thus those materials which are having capability to exist in the form of, or converts into the form of a liquid crystalline state, are highly stable in nature. The first type of the liquid crystal under thermotropic liquid crystal is the smectic liquid crystals. So though the name is telling that these materials are having liquid nature, that means they should have the nature of mobility, that is fluidity. So like normal liquids, the smectic liquid crystals will flow, but not as that of normal liquids. I mean, they cannot flow that much easily when you compare with a normal liquid or true liquid, because the smectic liquid crystals are having very limited mobility on account of their layered structure. So you can observe over here, the smectic liquid phase is having layered structure in this way, and the movement of this smectic liquid crystals is mainly due to gliding of these layers one over the other. And because of this gliding of the planes or sheets or whatever it may be, the layers on one over the other, the smectic liquid crystal will show some sort of mobility. But since the strong attractive force will be there between the layers, because of this, the movement of the layers is not that much free. That's why it do not flow like a normal liquid. And in case of liquids, we used to say one term called the laminar flow. That is, as you move from the fixed layer to the mobile layer, as you move up from the fixed layer to the mobile layers, there occurs increase in the velocity, and that's what we call as velocity gradient. That means there occurs distribution of velocities among the layers of the true liquid. And here in case of smectic liquid crystals also, we are having layered structure. And here also we can say the distribution of velocities from one layer to the other layer. And because of the distribution only, the layers, I mean to say one layer will glide over another. but we cannot compare the distribution of velocities of the different layers in case of smectic liquid crystals with that of true liquids. It's completely different. There, in case of true liquid, the velocity gradient will be more, but in case of smectic liquid crystal, the velocity gradient will be very less. That's why we are telling the smectic liquid crystals are having limited fluidity. And the flow of this smectic liquid crystals is completely non-Newtonian. That means we cannot apply the concept of viscosity for the movement of the smectic liquid crystals. Okay, and when you pass the X-rays onto the normal crystalline solid, we used to get X-ray diffraction patterns. So like a normal crystalline solid, the smectic liquid crystal also possesses or will show the X-ray diffraction patterns when you pass X-rays onto it. But the thing is, for a normal crystalline solid, the diffraction patterns will appear in more than one direction. But in case of smectic liquid crystals, the X-ray diffraction patterns are always in one direction. The reason for this is the complex internal structure of the smectic liquid crystals. Because of the complex internal structure, the smectic liquid crystals do possess only one directional X-ray diffraction patterns. And when the smectic liquid crystals are viewed in polarized light, so when you view the smectic liquid crystal in polarized light, and in polarized light, the smectic liquid crystals appear to have the fan-like structure. So it is the most important pattern of the smectic liquid crystals, which can be used for the identification of the smectic liquid crystals. And these smectic liquid crystals are the materials which will not be, they do not affected by the magnetic field. They do not affected by the magnetic field. Means the domains present in this smectic liquid crystals will not get disturbed with the applied magnetic field. That means they will not get deflect, the domains will not get orient in the direction other than the, or somewhat in whatever the direction, they won't get disturbed in the presence of external magnetic field. That's why we are telling they do not affect by the magnetic field. And if you come to some simple examples of this smectic type of liquid crystals, or the very best example for a smectic liquid crystal will be ethyl para-azoxybenzoate. Ethyl para-azoxybenzoate is one of the best example for the smectic type of liquid crystals whose transition temperature is around 114 degrees Celsius and its melting temperature is around 121 degrees Celsius. And if you go with one more example of a smectic liquid crystal, that is ethyl para-azoxycinnamate. It is another example for the smectic liquid crystal, which is having a transition temperature of 140 degrees Celsius. And when you go on increasing the temperature, when you go on heating this ethyl para-azoxycinnamate up to a temperature of 249 degrees Celsius, at this temperature, the liquid crystalline form of this material will get changes into true liquid. So these are some two examples which can give for the smectic liquid crystals. And these smectic liquid crystals will be used in hyperspectral imaging, that is in case of electro-optical devices. And this smectic liquid crystals will be used, to say the ferroelectric LCDs, what you call as liquid crystalline displays. Okay, so in those things also, this smectic liquid crystals are used. The second thermotropic liquid crystal is pneumatic liquid crystal. So these pneumatic liquid crystals will show fluidity almost near to the true liquids, but not exactly like a true liquid. They show near normal flow, near normal flow of true liquids, but not exactly near normal flow of true liquids. And compared to the smectic type of liquid crystals, these pneumatic liquid crystals will show more fluidity. Okay, so these pneumatic liquid crystal flow more readily than the smectic liquid crystals. So they can flow much faster compared to that of smectic liquid crystals. And we said the smectic liquid crystals are having a non-Newtonian flow, but this pneumatic liquid crystals are having Newtonian flow. That means, so the viscosity will be appear due to stress, and that's why we can apply the concept of viscosity to the pneumatic type of liquid crystals, but we cannot apply the concept of viscosity to the smectic liquid crystal since the flow is non-Newtonian. But the pneumatic liquid crystals are having Newtonian flow, and thus we can apply the concept of viscosity for its flow. But the viscosity of this pneumatic liquid crystals are low compared to the viscosity of the pneumatic liquid crystals are low compared to the true liquids. Compared to true liquids, the pneumatic liquid crystals are having relatively low viscosity. And compared to the smectic liquid crystals, let me say in this way, we said the pneumatic liquid crystals are having nearly normal flow as that of true liquids. So you can say they may have, you can imagine that they may have almost closer properties to that of true liquids compared to the normal crystalline state. But though they are having nearly normal flow rate of that same true liquids, but compared to the smectic liquid crystals, these pneumatic liquid crystals are more anisotropic in nature. Compared to the smectic liquid crystals, these pneumatic liquid crystals are more anisotropic. And we said the smectic liquid crystals are having, when the smectic liquid crystals are viewed through the polarized light, we said smectic liquid crystals are appeared to have fan-like structure. And when you view a pneumatic liquid crystal through polarized light, it appears to have, which one, the pneumatic liquid crystal is appear to have thread-like structure. Thread-like structure, that is to when viewed through polarized light. So this is a one simple difference we can say between a smectic liquid crystals and pneumatic liquid crystal. That is, the smectic liquid crystals are having fan-like structure in polarized light, and this pneumatic liquid crystals are appear to have thread-like structure when viewed through polarized light. And we said the smectic liquid crystals do not or they cannot be affected by the magnetic field, but this pneumatic liquid crystals do affected by the external magnetic field. And that's why in case of smectic liquid crystal, even though you are applying the magnetic field, the magnetic lines of forces as well as the the pneumatic phase will not get, the smectic phase will not get interact. So still the magnetic field applied also, the smectic liquid crystal will appear to be turbid. But in case of pneumatic liquid crystal, when you apply the external magnetic field, the pneumatic phase will be aligned in the direction of magnetic lines of force of the external magnetic field. And because of this reason, in presence of the magnetic field, the pneumatic liquid crystal is appear to be very clear and transparent. It's very clear and transparent in presence of magnetic field. But once you remove the magnetic field, again the pneumatic liquid phase will appear to be turbid. That means this is one property we can use to check whether the obtained liquid crystal is pneumatic or smectic. And if you go with some simple examples of this pneumatic liquid crystal, the examples of pneumatic liquid crystal will be para-azoxyanisole, which is having a transition temperature of 116 degrees Celsius and its melting temperature is 135 degrees Celsius. One more example we can give, that is para-methoxycinnamic acid, which is having a transition temperature of 170 degrees Celsius and its melting temperature is 186 degrees Celsius. And that's a bit of discussion, a brief discussion regarding pneumatic type of liquid crystals. And this pneumatic liquid crystals are used in alphanumeric liquid crystal displays, such as what the displays we use in case of wrist watches, that is to say digital wrist watches, in calculators, in digital window clocks. In all these things we used to employ this pneumatic liquid crystals. That is one of the major application of this pneumatic liquid crystal. The last type of thermotropic liquid crystal is cholesteric liquid crystal. These cholesteric liquid crystals are the materials which will show properties of both smectic as well as pneumatic. They show the properties of both smectic and pneumatic liquid crystals. And we can easily differentiate a cholesteric liquid crystal from that of smectic and pneumatic liquid crystal. That is, we said in case of a smectic liquid crystal, we said they are having layered structure. But in case of cholesteric liquid crystal, like a smectic liquid crystal, the molecules have been arranged in the form of layers only. But in case of cholesteric liquid crystals, the layers of the molecules are much more thicker than the smectic liquid crystals. That is, in case of cholesteric liquid crystal, the thickness of the molecules in the layer, that is the layer thickness of the molecules in case of cholesteric liquid crystals will be around from 500 to 5000 molecules per layer. This is the range of thickness of the molecules in case of cholesteric liquid crystals, which is much more higher compared to that of smectic liquid crystals. And like a pneumatic liquid crystals, the cholesteric liquid crystals also having thread-like structure. So these layers have been arranged in the form of small layers. I mean to say, so a small thread-like arrangement. But the thing is that which is having both the properties of smectic and pneumatic liquid crystals. One special property of this cholesteric liquid crystals is, unlike smectic and pneumatic liquid crystal, these cholesteric liquid crystals are optically active. They are optically active. And compared to the pneumatic liquid crystals, this cholesteric liquid crystals are having the property, that is, they are highly non-Newtonian with respect to their flow. They are highly non-Newtonian compared to that of pneumatic liquid crystals. And if you want to give a simple example for a cholesteric liquid crystal, the very best example is the cholesterol benzoate. Cholesterol benzoate is the very best example for cholesteric type of liquid crystal, which is having a transition temperature of 145 degrees Celsius and its melting temperature is 178 degrees Celsius. And these cholesteric liquid crystals are mainly used in generation of lasers. I mean to say, the laser of this cholesteric liquid crystals will be used as an optic fiber based temperature sensor. In a temperature sensors, especially which is optic based, in such kind of sensors, these cholesteric liquid crystals are used in the form of lasers. And that's about this thermotropic liquid crystals. If you feel my video is worthy and useful, like it, share it, and do subscribe to my channel. Thank you very much.